Leadership in just one day. Learn from world-class speakers and thought leaders across industries. Gain practical tools to amplify your influence and lead with confidence. Invest in yourself. Invest in your future. Register today for free. What could you do in one day? When it comes to how you spend your time, you want it to be intentional, impactful, inspiring, and you want your investment to be worth it. The Modern Lab Leader Online Symposium is your chance to unplug, refocus, and level up your leadership in just one day. Learn from world-class speakers and thought leaders across industries. Gain practical tools to amplify your influence and lead with confidence. Invest in yourself. Invest in your future. Register today for free. What could you do in one day? When it comes to how you spend your time, you want it to be intentional, impactful, inspiring, and you want your investment to be worth it. The Modern Lab Leader Online Symposium is your chance to unplug, refocus, and level up your leadership in just one day. Learn from world-class speakers and thought leaders across industries. Gain practical tools to amplify your influence and lead with confidence. Invest in yourself. Invest in your future. Register today for free.
Hi, I'm George Hammond, conference producer at Technology Networks, and I'm here to introduce our next talk, the use of thermal infrared cameras for pathogen detection on tomato surfaces in cold room environments. I'm also incredibly pleased to welcome Dr. Andy Moreno. Dr. Moreno is a bacterial surveillance system AI engineer at AME Certified PCR Laboratories. He has a breadth of experience in DNA, RNA, proteins, and building robust tools for life science applications. Andy has held positions in industry, government, and professional associations since 1988 and was awarded a PhD in molecular DNA testing in 2019. A very warm welcome to you, Andy. Following the presentation, we will also have a Q&A session, and we welcome any questions that you may have. Please ask questions using the Q&A system to the right-hand side of the video player. And without further ado, I will now hand over to Andy to begin his presentation.
Thank you, George. Today's discussion is on the use of thermal infrared cameras for pathogen detection on tomato surfaces in cold room environments. This is an experiment that actually has this agenda: a study abstract, executive summary, introduction, foodborne pathogens, enhanced practical method, AME proposed protocol, suggested future studies, and a conclusion. We also review materials, method positives, method negatives, application of thermal images, validation parameters, and how we can improve the quality of the product, its taste, and my contact information. A study abstract would hypothesize our theory that using thermal infrared cameras as a detection hotspot detector and a quantitative real-time polymers chain reaction sample collection and testing methodology are perfect for a verification as an effective method for detecting Salmonella on tomato surfaces in a cold room environment. Our theory is poised that screening tomatoes for thermal hotspots, in other words, the variance in temperature detection as a result of bacterial growth, that variance between the termination of the skin of the tomato and the enhancement of temperature detection on the bacterial growth area, would be an indicative area for potential contamination by bacterial pathogens, specifically in this case, Salmonella. The experiment was conducted and data collected at a Primus standard certified cold storage facility specifically for tomatoes. The experiment confirmed our hypothesis in many areas, although no actual or real-time hotspots were confirmed on our client product. The hotspots were confirmed on experimental detection for inoculated Salmonella areas in the collected and tested samples. The study suggests that further research can be identified and specified for organisms such as E. coli 015787 subspeciations, as well as Listeria, as including Salmonella as detected hotspots. Our future development planning includes the engagement of artificial intelligence software to enhance the detection analysis capabilities of our method. We believe that this would substantially increase the sensitivity of Salmonella detection. How? I'll review it further, but in summary, the detection methodology uses artificial intelligence using YOLO version 8 as a comparison and analyzing software over thousands of other similar images to extrapolate high percentage determinations of the presence of Salmonella. The executive summary is that we have often noted that the random grab sampling of samples, particularly in a cold room environment, is an unverifiable, unreliable methodology. The engagement of relatively inexpensive thermal infrared cameras to detect bacterial hotspots can be a substantial game changer to detect particularly Salmonella on tomatoes in a cold room environment. Again, the experiment was conducted in a Primus standard certified cold facility, which means that it's a certain specific level of food safety precautions. And the experiment, we claim, is successfully identified every hotspot with alerts for Salmonella species, later confirmed with quantitative real-time polymers chain reaction, also known as DNA testing, with a 99% specificity and sensitivity. Again, our postulate is that we feel, and we are currently soliciting a government research grant to apply artificial intelligence software algorithms to this issue to further refine our sensitivity and specificity of the pathogen suspect locations. Let me introduce again the concept that we as a research team have engaged, that pathogenic organisms like Salmonella, like E. coli, pathogenic versions of E. coli, Listeria, are crucial to determine and help public health. And annually in the United States of America, we have an estimated 48 million reported, or many cases are unreported, of food pathogen illnesses, people that consume food products that they assumed were safe and later discovered that they had suffered a food poisoning. The current, and I'm going to have to say the standardized grab sample collection methods do face challenges. That is the high, low, medium, front, middle, back of a pallet grouping is random. It is a grab sample to look for swabbings of these bacterial pathogens. This new technology of thermal infrared cameras can substantially increase this detection specificity. Foodborne pathogens like Salmonella do cause horrible diseases, also known as salmonellitis. Symptomologies include diarrhea, fever, abdominal cramps. Anybody that's ever had it will tell you it's horrible. And people with immunocompromised situations, young or old, will suffer significant health challenges and may even expire or die. So these detection technologies, the use of DNA testing is crucial because of its high specificity and its rapid turnaround time. This model that you see on slide 7 is the capturing of valid samples using traditional technologies of random grab sampling, also statistically modeled grab sampling. That's trying to do a better modeling of based on the product and time of season, its quality, and then a low resolution thermal hotspot that's using a very inexpensive, in other words, a low pixel rate camera, or a high resolution. They're much more expensive. So the radius between a low cost thermal infrared camera runs about $1,000, and then the high end could be as high as $50,000. So this study was using the lower end thermal infrared cameras. So this is a model, a picturesque description using pallets of tomatoes and a forward-looking infrared handheld camera capturing pictures which show the variance in temperature detection based on color remediation from very dark as the low and very bright to the high. Those sample areas were then collected using a swab sample, then using DNA testing within an hour using direct-to-PCR and making a determination based on those analyses whether or not to release the product or to hold it for further testing to prevent contamination by the consuming public. This is the model. Our theoretical design was to essentially capture samples from multiple pallets, a single pallet, or even a single box, or even a single tomato. The issue is to use a thermal infrared camera, capture the visual, make a determination based on the experience and training of the end user, and then either screen it using our proprietary testing for E. coli's pathogenic subspeciations, Salmonella species or Listeria species. In this case, it would be Salmonella. Make a determination whether we want to further test, hold the product for the market, or to release it because of a non-alert to detection of bacteria. This model also allows for further testing using culture media, which requires 2 to 7 days for confirmations, pulse field gel electrophoresis, also known as traditional DNA, or whole genome sequencing to further subspeciation and detection and restriction from the market. These are extreme measures which are normally not used in a production model where the determination is to sell or not to sell. So our suggestion for further studies includes the following: either an advanced pathogen detection methodology using our AI proprietary software and integrating that into the entire model to increase the specificity and sensitivity beyond the 90% range up to and including 100% with these historical visuals and cross speciation detections. So our conclusion is that as a result of our data that we captured, that the use of thermal infrared cameras to detect these bacterial hotspots and DNA testing using our methods with direct-to-PCR and salmonella-specific speciation detections in a cold room environment has proven very effective within the Primus standard, which means specific temperature ranges, sanitation, and other quality metrics. The findings of our research indicate that a AI-developed software would significantly improve the detection capabilities. Let's just talk a minute about our materials. Of course, a thermal infrared camera. We use the lower end, which is around $1,000 US. Calibration. We also used other calibration tools. We use our own proprietary quantitative real-time polymers chain equipment, which was formerly used by the US FDA and other foreign countries that we've consulted. A video algorithm software. This is what we're working with. The version was YOLO version 8. Our sampling tools included the sampling swabs. We also used a digital thermometer to detect as a confirmation the temperature ranges. Our method positives included that our system did not have any destructive value on the products. It was completely remote. There was no invasive screening for the tomatoes if there were no detections of hotspots. Also, it rapidly scans a large or high volume of the products. And it identifies hotspots rapidly, and it also looks for targeted swab areas. The swab sampling followed by quantitative real-time polymer strain reaction has been verified by our experiments. Now, the negatives that could be looked at would be the initial cost of the thermal cameras, particularly if it's a multi-shift facility, 24/7. Many of these facilities require multiple cameras and multiple backups in case of failures. It does require training, and the training can be for minimally trained individuals, may be somewhat challenging, but we feel that with sufficient training and certification, traditional cold room employees can handle and effectively use our method. Environmental temperature control and humidity variations can affect the readings of the thermal infrared cameras and lead to inaccuracies. This can be minimized, but of other issues can be detected, such as yeast and molds and fungi and other areas that could complicate the detection, but we found this to be inapplicable. So the application of thermal imaging, it monitors very quickly cold produce for these storage hotspots. The thermal imaging can detect also bruises and do a quality assessment, but that's not the coverage in this study. Thermal imaging can also detect heat loss or entry from packaging defects. So the validation parameters of today's study was the accuracy, high accuracy of the thermal infrared cameras, and verified DNA testing as the gold standard for bacterial detection. As we've noticed, when, as an ancillary issue, COVID-19 first struck, the gold standard was a culture media for 2 days. And after extensive experience in testing globally, the gold standard was transitioned to quantitative real-time polymer strain reaction because of its specificity and sensitivity and rapid turnaround time. Sensitivity, that means how many times does the test get it right? It's amazingly correct. Sensitivity also includes the opportunity of not getting it right. In other words, getting it wrong. What is that percentage? And that is extremely low. So the data recording, each picture that's taken with the thermal infrared camera is digitally recorded and can be numeralized. In other words, that has a date and a time. So that data can be used as comprehensive data recording for further study by scientists and production managers. Specificity, again, Salmonella cannot be allowed to be entered into human consumption, particularly through commercial vendors. As we move forward, our theory is that this method can be improved by verification. It also verifies that all tomatoes are not contaminated by the use of hotspots, thermal infrared cameras, quantitative real-time DNA testing, as well as spoilage Spoilage is an issue. And if that can be removed in the cold chain process, we will find a lot fewer contaminations to humans consuming the products. So indirect contribution could be to the taste. Now, what does taste have to do with pathogens? Pathogen contamination significantly may influence the taste or may not. But what we're finding is the flavor is retained better without pathogens, and also the texture. Spoilage could also be detected with hotspot, the yeast and mold detection. And the quality, again, will build consumer trust in the product if the consumer knows that this measure has been engaged as compared and contrasted with traditional methods of random grab sampling or blind grab sampling. So we believe that this method could be applied to several areas in farm production, field packing, cooling, the transport, the distribution centers, and the end user. This methodology of using thermal infrared cameras, along with quantitative real-time polymer chain reaction technologies or DNA testing, will significantly improve every step in the screening of products in the cold chain as we get products from the farm production areas into the end user arenas. So I'd just like to leave my contact information as the primary investigator. I'd like to thank the organization which is funding and supporting this information getting out. And we would encourage any further questions by any reasonable parties to learn more about this technology or our methodologies. Thank you very much.
Thank you
George?
so very much, Andy, for the fascinating talk. As with all the other talks in the event, we're likely going to have lots of questions come in from our audience. And I can see that we have received some questions already, so I'll move straight onto the Q&A now. So your first question, Andy, is which type of thermal infrared camera systems were employed in the study?
Good question, George. Here is our thinking. The thermal infrared detection technologies can range anywhere from a low-end import model from around $300, which has a very low pixel rate, and that's how the quantitative measure of the instrument to detect the specificity of the finite sample collection, up to and including $100,000. So in that range, we selected the range under $1,000. We used a particular model. It was the FLIR model, forward-looking infrared model. Radar is something that has been used significantly in the military for many years. So we picked the lower range as a more commercially viable. There are many options, some even attached to a mobile device, a phone. And that will do essentially the same job. But we've found that the capturing of an independent system as opposed to mobile phones has been the much more reliable industrial base application. Over.
That's absolutely fantastic. Thank you so much, Andy. And we have another question from our audience today, which is which products were screened in the study?
Well, George, in this particular experiment, only tomatoes, and these were called grape tomatoes of a yellowish red variety by our cooperating client. And they bring in products, 14 trailer loads a day. And they had actually inquired, Andy, is there any way for us to verify with higher specificity and sensitivity that our product's not contaminated? As an aside, this particular vendor had issues in the past with Salmonella. They were accused. They wanted to have something even better. So as a direct application, our team assembled this particular methodology. They were already using DNA sampling, but they wanted to make it even better. They asked, and we came up with the idea and concept and model of using thermal infrared cameras on the low end to verify and increase the sensitivity. Here in the United States, the government agencies are extremely interested, and other vendors, on this method. Over.
That's another fantastic answer. Thank you so much for clarifying that, Andy. I know our audience is excited to hear more about your study, and we do have some further questions on this. So your next question is, which stage in the supply chain was the product specifically screened?
Very good. As we look at that cold chain graphic that I had previously, displayed, the cold chain really begins where the product is grown. That's commonly known as the farm production site. Then it's either a field pack or machine harvested, and then from there it goes to a wash cycle. Usually my clients' products were washed, and then eventually it's packaged, palletized, and then shipped to a storage location. This study was performed in a third party, commonly known as a distribution center or cold room environment. Cold room is actually a very universal term, including but not limited to these distribution centers. It could be a grocery store chain, or it could be a large vendor like a Costco or Walmart distribution center, or it could even be a restaurant, or even in the cold chain, a consumer's personal refrigerator unit. So the issue is, can this technology be applied to those various areas where the temperature is kept between 38 and 42 degrees? Yes. And depending on the technological capabilities of the cold room management, again, they need to have DNA testing capabilities, but the hotspot detection methodology using thermal infrared cameras can be applied at multiple locations, George. Over.
Thank you, Andy. We still have time for a few more questions today. So moving on to the results side of your study, would you say that the obtained results were what you expected?
Yes. And George, I would outline that this particular vendor was extremely relieved because we did a real-time study. I did have some inoculated samples. A real-time study means we took actual product of one pallet of 40 for their daily production. And using the handheld infrared camera, each box had a venting or a viewing window carved out of each side. Using the camera, they took a picture of each of the displayed windows of the products of the cherry tomatoes. That process took about 5 minutes. So 5 minutes to get a 99% specificity and sensitivity for Salmonella picture for hotspot detection and DNA confirmation is a reasonable, given this particular client, calculation for cherry tomatoes. Now, I would be the first one to venture that it may not apply to cantaloupes, which was the subject of my doctoral dissertation after a horrible event in the United States where many people died from the Jensen Farms listeria outbreak. I would like to apply our study, and I'll be continuing our study with cantaloupes for one of the major producers here in the United States of cantaloupes, examining thermal infrared camera images of cantaloupes as they sit in pallets ready for market. The question, will it apply to every product, is unresolved at this time. I think a specific study would have to be for other products like carrots and other fresh produce held within the same temperature parameter, 38 to 42 degrees in a cold room. Why is that essential? It's because the thermal infrared camera detects variances in temperature measurements based on heat and presents to the end user a visual picture of the variances between a very bright and a very dim detection. And that is used in this model detection. Over. George?
That is wonderful to hear. Thank you so much, Andy. And one follow-up question from that we have from our audience is, how did your results differ from the previous testing methods?
Excellent question. Our client had a wash cycle. Now, and give you invariants, many fresh produce products are what are known as field pack. That means a field production worker or machine captures the product directly from the plant and puts it into a box in the field. The other side of that equation, or other model for sample preparation for market, is wash cycling. That means that the producer will take the product and run it through either a vortex water or a flume and had chemicals such as chlorine, chlorine dioxide, parasitic acid to wash the product to remove bacterial pathogens, or even just potable water, depending on the area. And that chemical concentration be anywhere from 200 parts per million, very dilute, chemical concentration to remove any bacterial pathogens, and then packaged and palletized. So this product we had assumed would be very clean because it had been washed in a flume. Parasitic acid had been applied in US FDA regulation. So we had assumed that we'd have a very tough time detecting anything. And we were correct. Now, we did inoculate several other samplings with specific concentrations from very low concentrations to very high, and all of the inoculated samples detected with the thermal infrared camera at a very economic thermal infrared camera. Had we used a very expensive camera, perhaps, and there is a question, would we have had increased detections? That's an unknown. My suspect apprehension is that maybe we would have had some detections if we had used a $100,000 camera. Of course, that's outside the operational range. And my theory is if the cold room had kept its food safety standard at those levels of temperature and maintained the cold chain, that those issues would not have been an issue for the end user as far as pathogenic cross-contamination. Over. Thank you, George.
That's fantastic. Thank you, Andy. And we have time for one final question before we close out this session. So what would you say are the main implications of this study for future food surface testing?
Well, my first and most important deduction from our study is that the current state of the industry and government regulation of random grab sampling has to be improved. We've had significant outbreaks of people actually being harmed. People have died, lost their livers, suffered significant debilitations from food poisonings. We have to, as an industry, as one human providing food for another human, increase our detection capabilities of bacterial pathogens on fresh produce. My theory is that washing product rather than compared to field packing is better. So my conclusion and recommendation to the industry is to engage in flume washing, packaging, palletizing, maintaining a food safety standard of cold temperature chain retention, as well as to consider thermal infrared cameras and DNA testing on every lot, not on a random or grab sample basis. Over. Thank you, George.
Thank you so much, Andy. Unfortunately, that is all that we have time for today. Any questions that we didn't have time to get to will be sent to the speaker after the event. And as of all the other talks in the event, this talk will now be available to view whenever you want for the next 30 days. That just leaves me to say thank you once again, Andy. It's been an absolute pleasure to have you present with us, and we really appreciate your time. And to everyone in the audience, we'll be back soon with the next talk.